Section 3.6 looks at a second order linear constant coefficient homogeneous equation. In other words, something of this form where m, b, and k are constants. For example, this could be the mass and frictional coefficient and spring constant of a spring. It'll also be a model for a circuit in chapter 4. In fact, in chapter 4, we're going to learn how to solve this second order problem when it's not homogeneous, when the right hand side is an exponential or sine or cosine or polynomial. Pretty much like in section 1.8, we learned how to solve a first order non-homogeneous problem, and a lot of the same techniques will apply in chapter 4. That is, the general solution will be the general solution of the homogeneous equation plus a particular solution, and you find the particular solutions pretty much the same rules as you did in 1.8. But right now we're only concerned with the homogeneous problem. In fact, this section kind of belongs more in chapter 4, it seems like, although you can reduce this to a system of two first-order equations, and we sometimes do that and solve it that way. But in this section, we're mostly actually solving it as a second-order problem. So it really belongs more in chapter 4 than chapter 3, which is about first-order systems. Okay, so how do we solve this constant coefficient homogeneous? That means the right-hand side is 0. Constant coefficient linear homogeneous second order equation involves a second derivative. Well, we try, they call it the method of the lucky guess. You try something in the form e to the pt, where p is a constant, and that's a good thing to try because first and second derivatives of e to the pt are just multiples of e to the pt, and you get second derivative is p squared e to the pt. First derivative is p e to the pt, and y is just e to the pt. So you can factor out e to the pt, and this has to be 0 for all t. The solution differential equation means it's true for all t, which means since this can't be 0, this constant must be 0. So mp squared plus bp plus k equals 0. And every time you see a problem like that, you can just go ahead and write down this characteristic equation. You know that solutions of the form e to the pt have to satisfy this quadratic equation. Well, there are three possibilities here when you have a quadratic equation. The discriminant could be negative, positive, or 0. If it's positive, that means we have two distinct real roots. We call them p and q, and then it's really simple because we know e to the pt is a solution. E to the qt is also a solution because that's another root. They're independent, they're not multiple of each other. So the general solution, just like a homogeneous first order system, is a linear combination of the two. So clearly any multiple, if e to the pt is a solution, any multiple of it, the constant just comes out, will also work, and you add two solutions, you still have a solution. So the general solution, which is what we need because we are going to have initial conditions, so you need a general solution, and there needs to be two constants in it because we're going to have two initial conditions. It's being a second order equation. So if p and q are two distinct real roots, then it's really simple: a e to the pt plus b e to the qt. And it doesn't matter whether p and q are integers, that is, are rational functions that they can have square roots in them, as long as their discriminant is positive and both roots are real, then it's real simple. Okay, then what if the discriminant is negative? That means you have two complex conjugate roots, alpha plus or minus beta I. Well, then a e to the alpha plus beta it is a solution, and a e to the alpha minus beta it, because p equals alpha minus beta I and p equals alpha plus beta I are both solutions. So that's a general solution, but that involves imaginary numbers. This is a real equation. We want a real general solution. So let's see if we can get rid of the complex numbers. And well, we use Euler's formula, just like in section 3.4, e to the alpha t times e to the beta ti. And by Euler's formula, that's cosine beta t plus I sine beta t. And then here, same thing, except e to the alpha t, e to the minus beta ti. And that is Euler's formula applied to minus beta ti. Cosine of minus beta ti is the same as cosine of beta ti, so cosine's even function. The minus just disappears. Sine of minus beta t is an odd function, so the minus comes out. Then you get the cosines, the e to the alpha t cosine of beta t's together, and you have a plus b. Get the e to the alpha t sine of beta t's together, and you have ai minus bi. Well, we're just going to call this first constant, say a and b are arbitrary. In fact, they'll normally be complex if you have real initial values, which you will. Alpha, a and b will normally be complex, but it's still just a constant. A plus b is some constant. ai minus bi is another constant. We'll just call those constants c and d, and c and d will be real, but they'll have to be because the real initial conditions, real equation. So even though a and b are complex, a plus b and a minus bi will turn out to be real. In any case, that's the general solution, and there's no complex numbers here. So basically, if you have complex conjugate roots, alpha plus or minus beta I, you can just immediately, you can skip all this, immediately write the solution is e to the alpha t cosine beta t and e to the alpha t sine beta t, and any intercombination of those. So two distinct real roots, the discriminant's positive, two complex conjugate roots, the discriminant's negative. If the discriminant is 0, that means you have one double real root, and in this case, of course, e to the pt is a solution because p is a root. The other solution, you need two independent solutions, and you get lucky that just when you need a second solution, t e to the pt is such a second solution. And let's verify that. That's not at all obvious. So since p is a double root, we know that e to the pt is a solution, but it's not obvious that t e to the pt is also a solution, so we have to verify that directly. Just plug t e to the pt into our differential equation. Here's the second derivative. We have to use the product rule a couple of times. Here's the first derivative. Use the product rule. Here's the function itself. Collect all the t e to the pt's together, and you have mp squared plus bp plus k, which is 0 because p is the root of that, exactly that quadratic. And get the e to the pt's together. Its coefficient is 2mp plus b. Now that's also 0. Why? Because p, since the discriminant is 0, the p is just minus b plus or minus 0 over 2m, so 2mp plus b is 0. So both of these are 0. So for all t, this is also a solution, and that's not just a multiple of that, so there's your general solution. So three cases: if you have a double real root, e to the pt and t e to the pt are the two solutions. If you have complex conjugates, e to the alpha t cosine beta t, e to the alpha t sine beta t are solutions. If you have two real roots, then that's easy. E to the pt and e to the other root qt are your solutions. Now let's do an example where we have initial conditions, so we have to find the general solution using one of these three forms, depending on what the discriminant is. And I'm doing problem 12 here. Y double prime minus 4y prime plus 4y equals 0. You can immediately write down the characteristic equation, p squared minus 4p plus 4. That factors as p minus 2 squared, so 2 is a double root. So this is the third case. There's your initial conditions. So a general solution, e to the 2t is a solution, t e to the 2t is a solution. General solution is a linear combination of those two. Now we have to adjust the constants so that you satisfy the initial conditions. For any problem, whether it's a system or single equation or first order, second order, when you have initial conditions or boundary conditions, basically it's the same procedure. You just simply have to have to adjust the constants so that those two are satisfied. And this says y of 0 is 1, so plug in t equals 0, and you get a times 1 plus b times 0, so that's just a, and that has to be 1. And then y prime, here's the derivative. That would be 2a e to the 2t is the derivative of that. This you have to use the product rule. It would be b times the derivative of t, which is 1 e to the 2t plus bt times 2e to the 2t. So that's the derivative. You have to actually calculate the derivative, then plug in t equals 0, and that'll be 2a plus b, and that's 0 because of the t there. So 2a plus b also has to be 1. So a has to be 1 and b has to be minus 1. And going back and plugging in a equals 1, b equals minus 1, there's your final solution. So the homework problems in section 3.6 are similar to ones I just did. You're going to have one case where there's two distinct real roots, one where there's a double root, and one where there's complex roots. And if there's complex roots, and if you have initial conditions, you're going to have to take the derivative, and it's going to be a bit of a mess and a little bit harder to solve for the constants, but it's straightforward. Just whatever the initial conditions say, y of 0 is 3, y prime of 0 is 11, calculate y of 0, calculate y prime of 0, and set them equal to 3 and 11, and there's your two equations.